Functions, functions, functions. We are about to start. Well, the beginning of when I liked mathematics. I hated math all the way through 10th grade. In 11th grade, I started to like it. In 12th grade, I absolutely loved it. And the difference was in 12th grade, my teacher, well, in 11th grade, there was a girl in my class that I had a crush on. That was why 11th grade I started to like it. Call it transference from the girl to the math. She was very good at math. And then the next thing is pre-calc with Mr. Braze, the one who says, "Oh, what are they asking for?" And he made the stuff come alive. No longer was it a bunch of rules laid down by a teacher who had no idea why any of this was important. All of a sudden, he was explaining it in such a way that it related to the world around me. It began to make sense. It was like, oh, God, this stuff was coming alive. I really like it. Because we all have functions, right? This red-bellied woodpecker, I'm sorry. Red-headed is more red in its head than this one. This red-bellied woodpecker, called because a part of its belly behind the log of that tree is red, has its function. Its function is to get larvae and insects out of the wood to hopefully prolong the life of the tree long enough. Everything has a function, and functions explain a lot about how the world acts, and beginning to understand functions in mathematical theory begins to understand the world. Now, let's be perfectly clear. You could take a course in functions. So we're not going to cover everything you need to know about functions, but we are going to give you a really good basis over the next two lessons. And as always, we begin our agenda with homework review. Well, we just went over that. The pregame stretch and going over that. Done. Now we're into recent work recap. A little bit of shift here into new type of questions. Let's try the first one. Okay, you're always doing the stop and start. I'll give explanations as it goes along, but let's evaluate each one of these. So a negative exponent, negative exponent, reciprocal, sir. Flips it upside down, so 1/4 becomes 4, and then to the first power it just stays 4. Number 2, anything except 0 to the 0 power is 1. We went over y earlier in the year. Number 3, 1/4 to the 1/2. Now the 1/2 power, we haven't talked too much about this, but the 1/2 power means square root. So the square root of 1/4 is 1/2. And 1/4 squared means a fourth times a fourth, which is 1/16. Which of these is largest? Choice 1. Ding, 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 ding. Okay. Factoring trinomials and using AM or the graphing calculator. Go ahead, factor these two. Okay, so for the first one, I need to multiply out to 35, add up to -12. What could that be? Oh, I know, -7 and -5, which makes the factors x minus 5 and x minus 7. Sorry for the yawns. According to the MacBook Pro in front of me, it's 10:25 p.m. on Thursday night, and I got to be up early to take a guy fishing Friday, and also another one on Saturday, and another one on Sunday. So I got 3 busy days ahead of me. So I need to get these videos up. It's now or never, as Elvis would say. I did a lousy impersonation. Let me try again. It's now or never. Oh well, that's why I teach math, and I better be decent at it because I was never going to make a living as a singer. Okay, what if I used a graphing calculator? Well, under y1, I would put the last number divided by x. That's 35 divided by x. And then, under y2, I put the same exact thing plus x. I look in the last column for a -12. The 2 previous columns would say -5 and -7. Okay, number 9. I need to multiply out to a -28, add up to 3. Oh, I know. -7 and 4. I have this backwards. Oh, no, I don't. I'm sorry. I have to add up to +3. For a moment, I was having a brain cramp and I thought it was negative. Yes, so it's +7 and -4. So that means the factors are x plus 7 and x minus 4. If I did it on the calculator, under y1, I put the last term divided by x, which is negative 28 divided by x, and under y2, I do the same exact thing, plus x. I look in the last column for a positive 3. The two previous columns will say 7 and negative 4 in either order. Okay, now those two factorings I think should be pretty simple. These factorings are more challenging, but we're starting to have done enough of them that I think we should be pretty good at it. Try these three to stop and start. Okay, so for this first one, I notice there is no greatest common factor. That's plan A. So I go to plan B, which is to multiply the last term by the leading coefficient. So that makes, I take this 2 in the front here, I multiply it by the 6, and I get a 12. Now just factor that as normal. That's x plus 3 times x plus 4. But we did change the question. So we have to go back in and reverse the question, or balance the question. And we do that by dividing both factors, the last term, by the 2 we multiplied by. So that gives me 3 over 2 and 4 over 2. Now 4 over 2, that's easy. It reduces to 2. Okay. And the other one, I have to use the elementary school trick we've spoken so frequently of, like improper fractions and mixed numbers. 2 times x is 2x, so I get 2x plus 3 times x plus 2. If I check back, 2x times x is 2x squared, 2x times 2 is 4x, 3 times x is 3x, 4x and 3x do indeed give me the 7x I was looking for, and 3 times 2 is 6. Bingo! Ding, 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 ding. All right, try number 9. Okay, so there is no greatest common factor. We go to plan B. Multiply the last term by the lead coefficient. So I take this 3 right here, multiply it by the negative 8. That gives me x squared minus 2x minus 24. Factor that guy right there. X minus 6 times x plus 4. But I have to balance it out by dividing back in by that 3 I multiplied by. So that gives me x minus 6 times x plus 4 thirds. And combining in one step, the 2 steps I did last time, 6 over 3 is 2, and then the elementary school trick, 3x plus 4. Multiplying back, x times 3x is 3x squared, x times 4 is 4x, negative 2 times x is negative 6x, and negative 2 times 3x, I'm sorry. Negative 6x and 4x adds up to the negative 2x I wanted, and negative 2 times 4 is negative 8. Last one, number 10, give it a try. Okay, so they all share a 5 in common, so let's factor it out. That's 5 times n squared minus 2n plus 1. I don't know why I put equals 0 there. Factor 5 times n minus 1 times n minus 1, and that's it. We're all done. Don't worry about the equal 0 or carrying it on. For some reason, I had a thought that this was equal to a quadratic equation, and it wasn't. It was just a factor guy. Okay. So there's a type of factoring, a special case that we really haven't talked about, and it's called the difference of 2 perfect squares. Now, let's talk about it now. It's honestly easier factoring. It's a special case, and this could have been taught years ago when I first learned this as if this was different from regular factoring. And some teachers teach it that way. They call it dots. Difference of 2. They kind of skip the P for perfect, and they go right to S for squares, D-O-T-S. I don't like to do it that way. You see, what this really is, x squared minus 25, it's really x squared plus 0, x minus 25. Just like x squared minus 9 is x squared plus 0, x minus 9, x squared plus 0, x minus 100, and 4x squared plus 0, x minus 1. Which means that I'm going to multiply out to the last term, which in the first problem, let's get back to that now, is negative 25, and add up to 0. And the way you do that is with a positive and a negative 5. These are easy enough that you shouldn't at all need a calculator. So you're really taking the square root of x squared, which is x, and that's where the 2 x's come from, and the square root of 25, which is 5 and negative 5. But the reason it works, if you check back, x times x is x squared. Okay, that's good. X times negative 5 is negative 5x's, and positive 5x's add up to 0x. The only way we can get a 0x is if these numbers are the same, except sign. So one's positive 5, one's negative 5, and as long as the x's are the same, you're going to get plus 5x's, minus 5x's, always getting 0x's in the middle. And then 5 times negative 5 is negative 25. So we don't bother writing the plus 0x. And sometimes that makes us think this is like this whole other way to factor. But that's not the truth. The truth is that it's a simple thing to factor, and there's a little bit of a shortcut that you can take because of the plus 0x we never really write. And that shortcut is, what's the square root of x squared? X and x. What's the square root of 25? 5 and 5. Make sure the signs are opposite. Plus 5, minus 5. Try the next one. Okay, so we know that they have to add up to 0x, and the only way to get that would be plus 3 and minus 3. The only way to get 0x is when adding is if the numbers are the same with the signs changed. So checking back, x times x is x squared, x times negative 3 is negative 3x's, 3 times x is 3x's, negative 3x and positive 3x add up to that mysterious, not written 0x that we're looking for, and 3 times negative 3 is negative 9. Okay, try the next one. So this strategy, it only works with perfect squares. So if I square root x squared, I get x, and if I square root 100, I get 10. So it's x plus 10, x minus 10. Checking back, x squared minus 10x plus 10x adds up to 0x's, and 10 and negative 10 make negative 100. Excellent. Try the last one. Okay, so here's where thinking of it as a square root might save you a little bit of agita. The square root of 4x squared is 2x. The square root of 1 is 1. So I get 2x plus 1 and 2x minus 1. Notice throughout all 4 of these answers, the x to 5, the x to 5, the x to 3, the x to 3, the x to 10, the x to 10, the 2x to 1, the 2x to 1. It's always the same numbers because they're square roots. So they have to be the same numbers because square root means the number that times itself. What changes every time is the sign in the middle. Plus, minus, plus, minus, plus, minus. If you wanted to do minus plus, that would be fine. Bottom line is, in each case, the signs have to be opposite so I can add up to those 0x's in the middle, okay? So let's add this to our factoring skills. And now we're going to talk about this word completely when applied to factoring, or more specifically,